Welcome to Evo AI, where we navigate the intriguing evolution of artificial intelligence. I'm your host, Bogdan Iancu, and in this series, we'll explore how artificial intelligence is transforming the way we work, innovate, and grow. From small startups to corporate giants, we'll unravel the mysteries of AI, uncovering insights, strategies, and the real-world impact on our everyday lives. Whether you're in sales, finance, marketing, human resources, or just curious about artificial intelligence, Evo AI has something for you. Hello everyone and welcome to AI Unlocked. Today we're exploring a particularly intriguing aspect of AI, which is its role in enhancing LoRa networks. LoRa, standing for Long Range, is a pivotal technology in the Internet of Things, or IoT, enabling devices to communicate over long distances while conserving power. As our world becomes increasingly connected, understanding the intersection of AI and LoRa networks is not just interesting, it's actually essential. We'll unravel how AI is revolutionizing these networks, making them smarter, more efficient, and ready to meet the growing demands of our connected world. Let's start then by exploring the significance, current applications, and recent advancements of LoRa, which stands for long range, and LoRaWAN, which is long range wide area network in the IoT landscape. LoRa and LoRaWAN are key players in IoT, offering low power, wide area network capabilities. LoRa refers to a specific radio modulation technique for long-range communication, while LoRaWAN is the network protocol that facilitates this communication. These technologies are vital for connecting devices over large areas, fulfilling IoT needs like bi-directional communication, security, and localization services. LoRa is particularly suitable for scenarios requiring wide range, low data volume, and minimal power consumption. LoRaWAN has emerged as a leading technology in driving the global industrial shift towards Industry 5.0, focusing on sustainability, efficiency, and quality of life. Its applications include monitoring gas leaks, water damage prevention in buildings, and ensuring residential privacy without compromising personal data. The IoT market, with LoRaWAN at its forefront, is expected to reach a global value between $5.5 trillion to $12.5 trillion by 2030. Recent innovations in LoRaWAN chipsets and devices have significantly improved power efficiency and extended device battery life. Devices like Curlink's WIRNet iFemtocell and Libelium Smart Agriculture Pro are prime examples of these advancements. LoRaWAN is recognized as a key tool in achieving environmental, social, and governance, or ESG, goals. Its low power consumption and secure data transmission make it ideal for applications in smart buildings, smart grids, and supply chains, and even more. Some recent developments here. Semtech has launched a new multi-band LoRa transceiver, the LR1121, enhancing global spectrum support and lowering power consumption. This development marks a significant improvement in LoRa technology, offering both better performance and versatility for IoT devices. The LoRa Alliance has introduced an accreditation scheme for developers and engineers, highlighting the growing need for skilled professionals in this field. This initiative aims to bolster the adoption and implementation of LoRaWAN technology globally. In conclusion, LoRa and LoRaWAN are at the moment at the forefront of IoT development, offering us innovative solutions for long-range and low-power communication. Their applications span diverse industries and are crucial in the transition towards a more connected, efficient, and of course sustainable world. We will cover now a more in-depth and technical exploration of AI's role in networking. And we will look briefly at advancements in AI algorithms for traffic management, machine learning in network configuration, deep learning for network monitoring, AI-enhanced security protocols, resource optimization, and user experience enhancement. Diving deeper into network traffic management, AI employs sophisticated algorithms like neural networks and decision trees to analyze and predict traffic patterns. These algorithms process vast amounts of data, learning from network behavior to optimize the flow of data packets. They can dynamically reroute traffic to avoid congestion, especially during peak usage times, ensuring efficient data transmission across network. In automated network configuration, machine learning plays a pivotal role. By continuously analyzing network performance data, these systems can adaptively tune network parameters. This includes optimizing router configuration based on traffic load, adjusting quality of service or QoS settings for different applications, and managing bandwidth allocation to prevent bottlenecks. The goal is to maintain an optimal balance between performance and resource usage. Proactive network monitoring leverages deep learning techniques to analyze patterns and predict potential failures. These models can process complex datasets, identifying subtle anomalies that might indicate a looming network issue. By forecasting these issues, the network can schedule maintenance and reroute traffic, thereby avoiding disruptions. In enhancing network security, AI algorithms are trained to detect a range of cyber threats, from DDoS attacks to unauthorized intrusions. By employing techniques like pattern recognition and anomaly detection, these systems can swiftly identify and isolate threats, safeguarding sensitive data. Moreover, AI-driven security protocols continuously evolve, learning from new threats and adapting their defense mechanisms accordingly. For resource optimization, AI systems use predictive analytics to anticipate network load and allocate resources efficiently. This involves not just scaling up resources during high demand, but also scaling down during low usage periods to conserve energy and reduce operational costs. AI-driven scalability ensures that the network remains robust and responsive under varying load conditions. AI significantly enhances user experience by optimizing network performance tailored to user behavior. It involves analyzing user data to prioritize network resources for critical applications and services. For example, AI can prioritize bandwidth for video conferencing during business hours while optimizing for streaming services during off-peak hours. This user-centric approach ensures that network resources are utilized effectively to meet user demands. AI, particularly through machine learning techniques, plays a significant role in addressing challenges in LoRa networks, which are crucial for IoT applications. These challenges include optimizing resource allocation, reducing latency, and extending battery life. The integration of AI into LoRa networks enables more efficient management of network resources, enhances the performance for IoT devices, and improves overall network reliability. Let's see how we can enhance LoRaWAN performance with machine learning. One of the primary applications of machine learning in LoRa networks is in resource management. Efficient utilization of radio resources like spreading factor and transmission power is crucial. Machine learning methods can dynamically optimize these parameters based on network conditions, leading to improved network performance. Machine learning algorithms can be used to determine the optimal spreading factor and transmission power for each device in the network. This optimization helps in balancing the trade-off between coverage, data rate, and energy consumption. For example, a higher spreading factor can increase coverage but also increase the time on air or TOA, which can lead to higher energy consumption. In dense network environments, collision and interference can significantly degrade network performance. Machine learning techniques can predict and mitigate these issues by optimizing channel access mechanisms and spreading factor allocation. For IoT devices, battery life is a critical factor. Machine learning can help in predicting the energy consumption patterns of devices and also adjust their operation modes accordingly. This approach can significantly extend the battery life of IoT devices. By intelligently managing the data transmission schedules and optimizing the network parameters, machine learning can help in reducing the latency in LoRa networks. This is particularly important for applications that require real-time data processing. Artificial intelligence can also play a role in enhancing the security of LoRa networks. By analyzing network traffic patterns, AI algorithms can detect anomalies that can indicate security breaches. This proactive approach to security can help in preventing attacks and ensuring the integrity of the network. AI can also predict potential network issues before they occur, enabling proactive maintenance. This capability is particularly useful in large-scale IoT developments where manual monitoring of all devices is actually impractical. The adaptive data rate mechanisms in LoRaWAN can be enhanced using machine learning. By analyzing the network conditions, machine learning algorithms can adjust the data rate dynamically, ensuring optimal performance across different network conditions. AI can also assist in network planning and expansion decisions by predicting future network load and performance. This foresight can help in optimizing the placement of gateways and other infrastructure components. Now, integrating edge computing with AI in LoRa networks can further enhance performance. By processing data locally at the edge of the network, the amount of data that needs to be transmitted over the network is reduced. This reduction not only minimizes latency, but also conserves energy and enhances security. Now, for those of you who don't know, we'll make a brief stop here to discuss edge computing. Edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. The basic idea behind edge computing is to process data near the edge of your network, where the data is being generated, instead of in a centralized data processing warehouse. Here are some key points about edge computing. Edge computing involves processing data as close to the originating source as possible. This could mean computing performed on a smartphone, an IoT device, or a local edge server. By processing data locally, edge computing significantly reduces latency. This is because the data doesn't have to travel over long distances to a central server or cloud for processing. And this is particularly beneficial for real-time applications like autonomous vehicles, industrial automation, or video processing, where quick decision-making is crucial. Transferring large volumes of data to the cloud can consume substantial bandwidth. Edge computing alleviates this by processing data locally, thus reducing the amount of data that needs to be sent to the cloud. Processing data locally can enhance security and privacy, as sensitive data doesn't have to be transmitted over the network. This is particularly important for applications dealing with personal or confidential information. Edge computing can increase the reliability of applications by enabling local data processing even when a network connection to a central server is unavailable or maybe unreliable. As the number of IoT devices grows, edge computing offers a scalable way to handle the increasing data volume by distributing processing tasks across numerous edge devices. Edge computing is increasingly being integrated with AI to enable smart applications in IoT devices. AI algorithms can run directly on edge devices, allowing for real-time analytics and decision-making. So, edge computing is a critical technology for enabling fast, efficient, and secure data processing in a world increasingly dominated by IoT devices and real-time data applications. It complements cloud computing by addressing its limitations in terms of latency, bandwidth, and of course, data sovereignty. Now, returning to our AI integration into LoRa networks, and as we have seen, such an integration offers a multitude of benefits, from optimizing network performance to extending the battery life of IoT devices. And as the IoT landscape continues to evolve, well, we need to note that the role of AI in enhancing LoRa networks will become even more significant, paving the way for more efficient, more reliable, and intelligent IoT solutions. Let's look at some real-world applications and case studies of AI-enhanced LoRa networks. And let's start with smart agriculture. And from smart agriculture, the first one that we'd like to cover is the precision farming. AI-enhanced LoRa networks are revolutionizing precision farming. By integrating AI algorithms with LoRa-based IoT devices, farmers can now monitor soil conditions, crop growth, and environmental factors in real time. This integration allows for precise irrigation, fertilization, and pest control, leading to increased crop yields and reduced resource waste. For instance, sensors deployed across fields collect data on soil moisture, nutrient levels, and weather conditions. AI algorithms analyze this data to provide actionable insights, enabling farmers to make informed decisions about crop management. Another one would be livestock monitoring. In livestock farming, AI-powered LoRa networks facilitate the monitoring of animal behavior and animal health. Sensors attached to livestock can track their location, movement patterns, and vital signs. This data, when processed through AI models, helps in early detection of diseases, efficient grazing management, and overall herd health optimization. Another one would be agricultural supply chain optimization. AI algorithms analyze data from LoRa-enabled devices throughout the agricultural supply chain. This includes monitoring crop storage conditions, transportation, and market demand. By predicting market trends and optimizing logistics, AI in LoRa networks ensures efficient supply chain management, reducing waste and improving profitability. The second one we're going to stop and look at would be smart cities. And what from smart cities? Well, the first one, waste management. Smart cities are employing AI-enhanced LoRa networks for efficient waste management. Sensors in waste bins transmit data on fill levels, enabling optimized collection routes and schedules. This not only reduces operational costs, but also minimizes environmental impact. Then, traffic management. AI algorithms process data from LoRa sensors placed throughout the city to monitor traffic flow. This information helps in real-time traffic management, reducing congestion and improving road safety. Additionally, it aids in planning urban infrastructure improvements. Then also environmental monitoring. LoRa networks equipped with various environmental sensors collect data on air quality, of course, noise levels, and weather conditions. AI models analyze this data to identify pollution sources and predict environmental trends, aiding in proactive urban planning and public health initiatives. And last and not least that I'd like us to cover in this episode is healthcare monitoring. And what from healthcare monitoring? Well, first one, remote patient monitoring. In healthcare, AI-enhanced LoRa networks enable remote monitoring of patients. Wearable devices equipped with sensors transmit patient data such as heart rate, blood pressure, and glucose levels. AI algorithms analyze this data for early detection of potential health issues, facilitating timely medical interventions. Then elderly care. For elderly care, sensors in homes monitor activities and health indicators. AI models identify patterns and anomalies, alerting caregivers to potential health risks or emergencies, thus ensuring the safety and well-being of the elderly. And last but not least, resource optimization in hospitals. Hospitals use LoRa networks to monitor medical equipment and inventory. AI algorithms predict equipment maintenance needs and optimize inventory levels, ensuring the availability of critical resources and improving healthcare delivery. Let's look now at some case studies covering all these three aspects that we talked about. One would be smart farming in Chile. A case study from MDPI covers in detail a significant project in Chile involving LoRa technology for agriculture. This project was focused on designing and implementing an IoT-based platform for remote monitoring of large-scale agriculture farms, enabling continuous data collection from IoT devices. The main objective was to modernize farm activity and improve management and efficiency through technology. Some key aspects of this project. The project is specifically aimed at large-scale farms in Chile, which are significant in terms of area and output. These farms often face challenges in monitoring and managing vast areas efficiently. The platform integrated a range of IoT devices, including sensors, actuators, meteorological masts, and drones. These devices were used to collect data on various aspects of the farm, such as soil conditions, weather, and crop health. One of the critical features was the ability to track labor activities in real time during harvest. This included monitoring people and machines for traceability and yield mapping. The project particularly focused on monitoring conditions for two fruit species, blueberries and Hass avocados, which are significant crops in Chile. The developed prototype offered a cost-effective way to access real-time data, which is crucial for making timely decisions in agriculture. The project emphasized creating a flexible platform that could be adapted to different scales of farms and various types of crops. The use of LoRaWAN, which is again long-range wide area network technology, was central to this project. LoRaWAN is known for its long-range capabilities and low power consumption, making it ideal for agricultural applications where devices might be spread over large areas and need to operate on battery power. The project included both simulation and experimental validation to ensure the effectiveness of the platform in real-world conditions. This project in Chile exemplifies how LoRa technology combined with AI and IoT can significantly enhance agricultural practices, especially in large-scale farming scenarios. It demonstrates the potential for technology to transform traditional farming methods, making them more efficient, data-driven, and sustainable. Another one would be the Smart City Initiative in Europe. In Europe, there are several notable cases studies of LoRa technology being used in smart city applications. Here are some examples. In Italy, in Bologna and Monte Carugolo, two smart cities testbeds were developed using LoRa and IEEE 802.15.4 technologies. The first one, which is in Bologna, focused on smart technologies for public lighting and smart building applications. This project utilized LoRa's long-range communication technology to address smart building applications in a real urban scenario. The second testbed is in Monte Carugolo, involved a large-scale implementation of a public lighting infrastructure with around 3,000 street lamps installed over a 211 square kilometers area. This infrastructure, operational since 2014, uses LoRa technology for wireless communication and the provision of smart services. Smart Santander, which is in Spain. Although not exclusively using LoRa, Smart Santander in Spain is one of the largest testbeds for smart city technologies, including IoT deployments. It involves around 3,000 devices, providing insights into smart city applications like environmental monitoring and urban mobility. Another application in Italy, in Cagliari, over 500 SenseCap LoRaWAN devices were deployed to address challenges like, for example, urban heat waves. This project is an example of how LoRa technology can be used for environmental monitoring in urban settings. These case studies demonstrate the versatility of LoRa technology in addressing various smart city needs, from public lighting and building monitoring to environmental management and also urban heat mitigation. The use of LoRa in these projects highlights its effectiveness in providing long-range, low-power communication solutions that are essential for smart city applications. And last but not least, healthcare monitoring systems in Asia, which is another article from NDPI called A Survey on Wireless Wearable Body Area Networks, a Perspective of Technology and Economy, provides a comprehensive overview of the deployment challenges and economic aspects of wireless wearable body area networks, or WBANs. There are some key points relevant to the healthcare monitoring system in Asia using LoRaWAN-based WBANs. First of all, the deployment of wearable or body-worn devices is increasing rapidly, attracting significant interest in technical and economic issues such as networking, interoperability, security, power optimization, business growth, and also regulation. WBANs are extensively used in healthcare systems. They involve sensors that can monitor vital health signs like body temperature, blood pressure, respiration rate, skin perspiration, blood glucose, heart rate, oxygen saturation, and electrocardiogram or ECGs. The data collected by these sensors can be transmitted to healthcare providers, allowing for real-time monitoring of patients' health. This is particularly beneficial for remote patient monitoring, elderly care, and also for managing chronic conditions. WBANs consist of a control unit and sensors which might be implanted in the body or be wearable. These sensors communicate with each other or with the control unit using a wireless link. The sensors used in WBANs are categorized based on their implantation and functions, including implantable sensors like pacemakers, ingestibles like imaging capsules, injectables like pH sensors, and patchable body surface sensors. The study also focuses on the economic aspects, including the compound annual growth rate of these devices in the global market and different regulations of wearable wireless body area network devices in various regions and countries. The use of WBAN devices enable physicians, fitness trainers, and coaches to treat their clients more effectively. The article discusses open issues and further research directions in the area of wireless body area networks, indicating ongoing development and improvement in this particular field. The study provides a detailed understanding of the technological and economic aspects of WBANs, highlighting the significant role in healthcare monitoring in Asia, but not only. The use of LoRaWAN based WBAN in healthcare monitoring is a part of a broader context of WBAN applications in healthcare. Concluding, all these real-world applications that we covered here and also the case studies illustrate the transformative impact of AI-enhanced LoRa networks in various sectors, driving efficiency, sustainability, and hopefully improved quality of life. Let's talk about some challenges and limitations in deploying LoRa technology and AI integration. So what are the challenges in deploying LoRa technology? Deploying the long range or the LoRa technology, which is a low power wide area network or LPWAN communication protocol, involves several technical challenges. LoRa operates in the ISM band, which is unlicensed and shared with other technologies. This can lead to potential interference issues. LoRa's use of chirp spread spectrum or CSS modulation helps in making it more resistant to interference, but risks remain, especially in widely populated areas where multiple networks might overlap. Establishing a LoRa network requires careful planning in terms of network management, resource allocation, and consistent communications. The need for a robust and secure infrastructure is paramount, especially considering the increasing number of devices and the data they generate. In LoRa deployments, managing energy efficiency is crucial, particularly for battery-powered devices. The trade-off between energy consumption and network coverage is a significant challenge. Since LoRa operates in the unlicensed spectrum, it must comply with various regional regulations, which can be a challenge in terms of network setup and operation. What about technical and ethical challenges in AI integration with LoRa networks? Integrating AI into LoRa networks brings its own set of technical and ethical challenges. With AI processing large volumes of data, ensuring data security and privacy becomes a critical issue. This includes safeguarding against unauthorized access and ensuring that sensitive information is handled responsibly. AI algorithms can be resource intensive. Running these algorithms on devices that are typically low power and have limited processing capabilities possesses a significant challenge. Ensuring the reliability and accuracy of AI-driven decisions, especially in critical applications like maybe healthcare monitoring, is essential. This involves continuous testing and validation of AI models. The use of AI in decision-making processes raises ethical concerns, particularly regarding bias and transparency. Ensuring that AI systems are fair and do not perpetuate existing biases is a significant challenge. AI systems must comply with various regulations, including those related to data protection and privacy. Navigating these regulations can be complex, especially when deploying systems across different regions. Integrating AI into existing LoRa networks requires careful consideration of compatibility and interoperability issues. Now, before we move forward, let's break down a few terms that we've just introduced before. Chirp spread spectrum, or CSS, is a modulation technique used in wireless communication, which is particularly effective over long distances and in noisy environments. In CSS, data is transmitted using chirp signals, a type of signal in which the frequency increases or decreases over time. The main advantage of CSS is its robustness against interference and multipath fading, which is common in wireless communication. This makes it ideal for applications where reliability and long range are crucial, such as in LoRa networks. In LoRa technology, CSS allows for a trade-off between data rate and sensitivity. By adjusting the chirp parameters, it's possible to optimize for a longer range, which is at the cost of data rate, or a higher data rate, which is at the cost of range. ISM band. The ISM band, which means the industrial, scientific, and medical band, refers to a set of frequency bands designated for the use of radio frequency or RF energy for industrial, scientific, and medical purposes other than telecommunications. These bands are typically unlicensed, meaning that they can be used without a radio license, but they must adhere to certain power and usage restrictions to minimize interference. Common ISM bands include 2.4 GHz used by devices like Wi-Fi routers and Bluetooth devices, and sub-gigahertz frequencies like 868 MHz in Europe and 915 MHz in North America. LoRa technology often operates in these sub-gigahertz ISM bands, benefiting from their long range and penetration capabilities. Last term that we've introduced is the Low Power Wide Area Network, or LPWAN. A Low Power Wide Area Network, or LPWAN, it's a type of wireless telecommunication network designed to allow long-range communications at a low bit rate among connected objects like sensors and actuators in an IoT network. LPWANs are designed to provide wider coverage area compared to a traditional wireless network while maintaining low power consumption, making them ideal for IoT devices that need to send small amounts of data over long distances. Examples of LPWAN technologies include LoRaWAN, based on LoRa, NB, IoT, and Sigfox. These networks are used in various applications such as smart cities, industrial monitoring, and agricultural sensors, where devices often run on batteries and need to operate for years without replacement. In conclusion, while deploying LoRa technology and integrating AI within its networks offers numerous benefits and advantages, it also presents several challenges that need to be addressed. These challenges range from technical issues like spectrum interference and network infrastructure to ethical considerations in AI deployment. Addressing these challenges is crucial for the successful and responsible deployment of LoRa and AI technologies. Let's talk now about the future prospects and developments in AI advancements in LoRa networks, and let's analyze some of the areas where significant progress can be expected in the next years. Enhanced AI-driven network management. Future LoRa networks are likely to see more sophisticated AI-driven management systems. These systems could use machine learning algorithms to continuously monitor network performance, predict potential issues, and dynamically adjust network parameters for optimal performance. This could include adaptive data rate control, intelligent channel selection, and predictive maintenance schedules for network hardware. Advanced edge computing capabilities. The integration of edge computing with LoRa networks is set to advance significantly. Edge devices equipped with AI capabilities will be able to process data locally, reducing the need for constant data transmission to the cloud. This local processing can include real-time analytics, immediate decision-making, and even local AI-driven control loops for IoT devices, greatly enhancing the responsiveness and efficiency of LoRa-based IoT systems. AI in energy harvesting and management. Energy management is crucial for the longevity of LoRa devices. Future developments may include AI algorithms optimized for energy harvesting and power management. These algorithms could intelligently manage the energy consumption of devices based on their usage patterns, available energy sources like solar or kinetic energy, and the network's overall energy status. Improved security protocols with AI. As LoRa networks become more prevalent, the need for robust security protocols become more critical. AI can play a significant role in enhancing network security. This includes the development of AI-based intrusion detection systems that can identify and mitigate threats in real time, advanced encryption techniques that adapt to the level of threat, and AI-driven security audits for continuous network security assessment. AI-enhanced signal processing techniques. Signal processing is a key component of LoRa technology. Future advancements may include AI-enhanced signal processing techniques that can adaptively filter noise, compensate for signal distortion, and improve overall signal quality. This would be particularly beneficial in challenging environments where signal interference and attenuation are common. Research in AI-driven predictive analytics. Predictive analytics using AI will become more prevalent in LoRa networks. This involves using AI to analyze data trends and predict future events such as equipment failures, environmental challenges, or network congestion. By anticipating these events, network operators can take proactive measures to prevent issues, optimize network performance, and improve overall service quality. Development of AI-optimized LoRa protocols. The LoRa protocol itself may evolve with AI optimizations. This could involve AI-driven algorithms that optimize packet size, transmission frequency, and other protocol parameters in real time based on current network conditions, usage patterns, and application-specific requirements. These developments suggest a future where LoRa networks are not only more intelligent and efficient, but also more adaptable and resilient. The integration of AI into LoRa networks promises to unlock new capabilities and new applications, making it a key technology in the evolving landscape of IoT and wireless communication. Today's episode of AI Unlocked has taken us on a comprehensive journey through the intersection of AI and LoRa networks, highlighting the significant advancements and potential in this exciting field. We began by exploring the basics of AI networking, emphasizing its role in optimizing network performance and efficiency, AI's capability to perform predictive maintenance, and sophisticated data analysis is transforming how networks operate, making them more efficient and reliable. Then we delved into AI's role in enhancing LoRa networks. We discussed how AI addresses challenges like latency and battery life in IoT applications, and how edge computing is pivotal in reducing data transmission, minimizing latency, and bolstering security in LoRa networks. Our journey continued with real-world applications and case studies where we saw AI-enhanced LoRa networks in action across various sectors like smart agriculture, smart cities, and healthcare monitoring. These examples illustrated the practical impact and versatility of AI in improving efficiency and functionality in diverse settings. We also addressed the challenges and limitations of deploying LoRa technology and integrating AI within these networks, from spectrum interference to the need for new network infrastructure, and from technical to ethical challenges in AI integration. We covered the complexities and considerations essential for successful implementation. Looking ahead, we speculated on future AI advancements in LoRa networks. The potential for novel physical layer designs, efficient data aggregation, enhanced security protocols, and advanced edge computing capabilities points towards a future where LoRa networks are smarter, more efficient, and more adaptable. As we wrap up this episode, please remember to subscribe to our website on evoai.ai and remember to follow us on Twitter and LinkedIn. You can find all our episodes on Spotify, Apple Music, Google Play, Amazon Music, iHeartRadio, and Radio Public. Your insights, questions, and feedback are invaluable to us as we continue to explore the ever-evolving landscape of AI and machine learning. Share your thoughts, experiences, and queries with us, and let's keep the conversations going. Thank you again for joining us on AI Unlocked. More from us soon. Until next time. Well, that's a wrap of today's episode of Evo AI. We've delved into the fascinating world of artificial intelligence, unlocking insights that are changing the face of business today and tomorrow. But the exploration doesn't end here. There's always more to discover. Well, I'm Bogdan Iancu, and this has been Evo AI. Together, we're part of something bigger, much bigger, a movement towards understanding, innovation, and growth. Well, if you enjoyed our journey today, don't forget to subscribe, and please join us again as we continue to explore the future of AI in business. Until next time, keep evolving.